Hi, Oliver. What's up?
Hey, Chrysanthos, how are you?
I'm good. I'm good. Thanks for the invitation to present today.
Sure. Thank you for taking time to visit us. I really want to meet with you too because I think your research on this supply chain optimization, especially now, of course, with I don't know if you do anything with the code supply chain and also even to the nanomaterials level. It's really fascinating to me. So that's why I would like to meet and learn more about. So maybe it's kind of
Yeah. Let me synopsize a little bit. So on the supply chain side, I mean, when you are a young professor, the chips fall where they fall, right, based on funding, etc. So in my case, what has occurred is that a significant fraction of my research ends up being in last mile distribution optimization. So essentially,
that's quite transportation related.
vehicle routing type of work, where we do quite a bit of work on developing exact methods like branch and price type methods. And I'm also methodologically very much interested in how do I bring robust optimization to do VRP under uncertainty. And the reason the chips have fallen there is because, we have this center at CMU. It's an industrial consortium with mostly the chemical process industry participates there, but the chemical process industry, does operate its own. Many of those companies do operate their own kind of logistics networks, and they even own fleets of trucks, etc. So decision-making problems in that space that come from the business go to essentially the chemical engineers, if you will, that are the optimizers in the R&D department. So they eventually come to us. So there's quite a bit of interest within the CAPD, the Center for Advanced Process Decision Making, for routing optimization, and that's mostly what I do. Of course, I also do more traditional planning, scheduling type of work, and then going down the length scale, as I'm going to present it later. I mean, chemical process design, all the way down to trying to apply mathematical programming type work, type approaches in the space of nanomaterials.
I see.
So for the design of nanomaterials, where we work a lot with computational chemists who have, if you will, domain expertise on the materials themselves, and are able to inform us on structure function relationships that are required, to do design. So they solve the forward problem, and we try to help them on solving the inverse problem. So I know you do work on transportation too.
Yes.
From my perspective, I'm a chemical engineer by training, right? And all my formal preparation is in that. And of course, I sit in a department of chemical engineering. So, but I'm very active, let's say, with Inform's TSL. I would go to the vehicle routing type conferences typically. So not just the TSL workshops, but also the Chrysanthos, Odysseus, and this type of conferences. And then but I'm probably the only chemical engineer there.
That's very exciting because all those traditional engineering fields, especially like chemical engineering, and I feel like the supply chain wide optimization seems to have a lot of potential power to either for saving costs or improving efficiency. And especially one thing, since you talked about chemical engineering, this reminds me of two things. One thing is really about transportation of hazardous materials, right? That's in transportation. It's really how do you minimize the potential health impact to the communities? That's a constraint. Another thing is really if you think about vaccine distribution, the cold chain. So do you by any chance touch upon those two areas?
I don't touch upon those. A colleague, Nilay Sat, Imperial, and works on supply chains for highly perishable materials and healthcare related materials like vaccines, as you pointed out.
Yeah.
And I do know that within the VRP community, the VRP community is very good at defining variants of vehicle routing type problems. And
yes.
There is a big trend right now, as you probably know, on VRPs augmented with constraints and rich features that have to do either with the environment like pollution routing type work, as well as with this notion of perishable material, so time-sensitive distribution, essentially.
Yes.
So that's that. There's also the concept of emergency logistics and like the idea of prioritizing, your service within, prioritizing different customers based on the need for service, and that's for emergency logistics type of application, or relief logistics, relief operations. But those are very, very interesting topics, and as you know, VRPs are notoriously hard to solve, right? They're not your archetypal. Typically they admit some sort of MIP formulation, but they're very far from being solvable with vanilla commercial algorithms. So they do require, some technology to be built up, in terms of customizing the algorithms with VRP specific cutting planes, or specific, you go to branch and price, like pricing routines and so on and so forth. And then how do you adapt all of that to address these new rich features that industry presents to you? It's always an interesting methodological challenge, and it's a good space to be at. I have found it very rewarding. I get students learn a lot about advanced mixed integer programming by working in these types of problems, and that's a good thing.
That's wonderful. So I think you touched upon it very briefly. So in all these, chemical and linear supply chain, as well as perishable product. But another thing I'm interested in is how in your community, in your risk community, how is this green supply chain concept? Is this the concept green supply chain, is that catching up with some momentum, or if you feel still, for especially with your center, you're working responding to a lot of corporate, their needs. So from your practice, did you see any trend of people becoming more concerned about or interested in green supply chain?
Yes, that's a very good that's a very good question. The thing I have to say is the following: they are all aware. They are all interested, not just in green supply chain, but on issues of sustainability more broadly, and that extends also to their manufacturing practices. And there is a lot of optimization that can be done to make those, highly polluting chemical plants, produce at the same rate, at the same efficiencies, but in a greener way. But on the issue of green, let's say, supply chain, there is not much incentive in place, regulation in place.
I see.
To make them actually implement these types of solutions, but they are certainly interested in it. They want, they look ahead. They know this is coming. They're going to have to operate in a society that is more sensitive to these issues. And from that perspective, they are maybe not down directly at the business level, but at the R&D level, they are certainly kind of thinking about these questions. I don't know if we recently had a seminar. Actually, last semester we had a seminar by Asa Pajic from UMIST in England. She is a big person in sustainability, not so much supply chain, but questions of the life cycle analysis type questions. They become much more prevalent in the area that in the communities I typically engage in. But again, I think it is more about exploratory type work.
I see.
And less so work that follows the business need at this point. At least that's my take.
I think that's a very Chrysanthos. I think that's a very realistic characterization of the current status. And I think you're right, because even these stakeholders, they are looking ahead. However, if there's no either incentive nor regulatory force, and then they're not going to do that, right? So I think that makes perfect sense. So of course, I think in your community, especially I think in chemical engineering, And I believe, not many people are doing things like you are doing. In chemical engineering, they are probably still, conventional chemical engineering. So with that, but on the other hand, I feel for all those big corporates, I think it's really your work that can give them a lot of leverage in either reducing cost or improving their profitability. So in your view, now I want to check with you about education. Like, what do you see as a major trends in this chemical and or even energy related industry in terms of their education needs? Imagine if we're thinking about our education programs, either for chemical engineering or system engineering, what do you see as a emerging market demand, and also correspondingly, what do you see as some curriculum change that we need to think about?
Well, okay, yeah. So we are actually in the midst of a big conversation in our department about that. In our case, and I think it's also case by case in as much as it depends on the historical trajectory of each department, right?
Yes.
But in our case, one of the biggest gaps we have identified in the undergraduate curriculum is the mathematical rigor that the students get. And it's a bit of a paradox in the sense that what happens, let's say at CMU, we get very, very good students, and it's competitive to get in on the undergraduate level. We don't handle admissions, but we know it's competitive. And a lot of what we get is a lot of kids who have done a lot of AP coursework, for example, in high school. So there are stellar high school students, but then they come to CMU and now they are exempt, let's say, from a couple of math courses. And then there is not enough. There is not a good process in place, I would say, to ensure that the kids now, since they get relieved from a couple of math courses because of their AP credit, there is not a good mechanism to figure out or impose for them what they do with this free time. So some students use it constructively to, let's say, go towards more specialized math classes and fill in their otherwise math, classwork with math content. Some others, just see it as an opportunity to explore horizontally. And that's also, there is also value in that. But at the end of the day, what they end up missing is the formal, rigorous university level math preparation that's necessary. So I teach a senior level class, introduction to optimization, essentially. Which requires, I try to cover pretty much everything, like LP, MILP, basic, the most basic of everything, and NLP. But that requires, basic skills in linear algebra, in calculus. And then they come to my senior level class, and then I have to actually review a lot of content that I would view is like high school / freshman kind of content. And then the argument, is that, but professor, last time I did math was 3 years ago.
I see.
So we see that gap in engineering, and we are not formally on the hook to teach them calculus 1, 2, 3, 4, right? But the way the whole system works, and I think this is also representative. I don't know if it's happening at Cornell specifically, but I'm pretty sure it's happening on other R01 type universities as well, and that creates a gap. So what we have tried to do now is take over numerical methods classes, and also put a lot of machine learning content in that class, and provide some formal preparation like that. In addition to us teaching the optimization class, which it is a little bit distinctive in a chemi curriculum, have a dedicated class for optimization. We call it optimization modeling and algorithms. So despite our focus, also due to our kind of pedigree with quite a bit of systems component in the department, we also feel the pain of, I think, lack of mathematics rigorous preparation on our engineering population, on our engineering students. And I think that translates eventually to things like you get fewer US educated students moving to grad school and doing computational work there. Like if you look at, I'm pretty sure it's the same case at Cornell. You do have a lot of solid, really great US students, you have some solid international students, but if you now break them down into their interest in terms of following experimental versus computational work, you will see a statistically significant kind of difference. And that I think eventually is because of, you know, how undergraduate education has evolved in the United States here. So the system needs to incentivize more of that.
Yeah, that's true. That's true. And I really appreciate, you know, you emphasize this mathematical rigor. And that's actually in the past few decades, even a lot of R1 universities, you know, I feel a lot of programs are becoming, you know, mathematically loose. Right. So from our high school and then of course to undergraduate school. So I think in that case, actually, if, you know, universities like CMU and Cornell, you know, because we have, you know, strong engineering colleges, if it takes advantage of, you know, the existing engineering strengths, if we develop that area, I think that could be really a good opportunity.
I think so, indeed. I think the program you specifically have over there, a very interdisciplinary program, with systems, you know, leading with the brand of systems, I think sets the tone and provides a very good example. We don't have something similar at CMU. We have a very strong systems cluster within chemical engineering. We have some colleagues in other engineering departments who are interested in decision making and look at systems view of their domain or in applications within their domain, and then we also have an OR program, and that's it. And we haven't come together across departments to form something of that caliber, and I think it's really great that you have that.
I see. Yeah. So you know, that's great. So you know, I'm really looking forward to a talk because, you know, when I'm looking at the topic, it's really going to be very related to my research area. I think it's really exciting. So, yeah. So do you have any questions?
Yeah, what I've created is essentially I wanted to point out that as chemical engineers, we apply optimization across multiple scales that really go down to the domain of chemistry all the way up to the, you know, enterprise-wide optimization, right? Including supply chain optimization. And I just basically what I did, I selected 3 vignettes from the 3 different scales, like large scale, small scale, medium scale. So it's not really the breadth of everything we do. One of the 3 examples I'm going to talk about is essentially how can we help. It's about routing, but we're developing some techniques to answer certain strategic questions for companies, not so much operational. Like it's not so much an algorithm to be used for operational routing day in, day out, but rather help them understand if their supply chain should shift to a more flexible customer kind of paradigm. So the main idea there, I'm giving you a preview, I guess. The main idea there is that, as you know, the way most last mile distribution networks operate is that the day at which they serve a customer is not very much flexible on an operational level. It's either a vendor managed inventory customer, but the selection of the service frequency has been done at the planning level, and then it's fixed day in, day out. Or you know, it's ad hoc customer that calls in and places an order, right? And then you kind of promise next day delivery. And that's how certain supply chains operate. And what we were trying to investigate is like, what if your customer affords you some flexibility on what day to actually deliver? And then you co-optimize that flexibility with your actual routing optimization, and you see that you have certain savings. And then now it opens up, if you will, a rubric. It provides you a rubric or at least some insights about entering a negotiation phase with your clients and giving them maybe a discount to incentivize them to accept the flexibility. So I'm tying. So although really the expertise there is on the last mile distribution optimization, we are carefully kind of employing those capabilities to answer more strategic question, which is, does it worth going flexible customers? And if so, how much can we afford to give them a discount? To what? How much discount do we afford to give them to actually incentivize them to accept it? So that's actually one of the 3 vignettes I want to talk about. So I gave you a preview, but I think you might find that interesting and close to your domain.
Oh, absolutely. Chrysanthos, actually, I think 2 points. So for the way you just talk about this last mile, of course, your clients, mostly the chemical engineering companies. But I just want to let you know, actually, your methodology can not only be applied to transport we call freight transportation. Actually, the chemical engineering is only a part of the freight transportation. Another thing is really this first last mile. Have you ever thought about transit? For transit, people need to go from their home to get to the transit station. And after get off the transit, they need to get to their office. This is also first mile, last mile. And also there is very interesting mechanism design. How can we, design the incentive such that, because from transportation, we're trying hard to move people from cars to transit.
True.
And the major difficulty in transit is the first mile, last mile.
Yes, and that's where a lot of interesting. So there's another big class of problems, right, that have to do with network design. So, and there are tons of interesting questions of how do I design my mass transit networks that are essentially flexible and they can better serve the distribution of needs of, how do they basically facilitate efficient and hassle-free first and last mile segments, which further incentivizes the people to switch to the mass transit transportation. These are super important kind of problems as well. They would fall in the category of network design.
Yes.
Not so much on the routing optimization, in as much as you are designing at the planning level fixed routes to eventually be able to take up the service load, rather than given the service load, define a custom build route for the day off. Yeah. Trying to minimize, actual costs of operating the fleet of delivery agents, essentially. But it's freight. It's mostly freight what we do, but it's also, it could be viewed also as services, right?
Yes. Yeah.
The routing of experts to clients to do service. Mm-hmm. And there are also extensions. So these routing type algorithms actually can address actually questions in the design of large-scale integration chipsets, like CPUs or whatever. And I'm not an expert in that domain, or even in human genome sequencing. These types of problems actually have relation to some of the problems there relate to traveling salesman and other generalizations of that, which is essentially routing. So there is broad interest in that field as well. And TSL, you're rightly to point out, is pretty much both transportation and the people that are doing vehicle routing, right? It's
That's wonderful. So this is great. I really appreciate your time, and I know, we can probably stop here so that you have time to prepare your talk. About half an hour. So I'll be really looking forward to a talk. And again, thank you for taking your time.
No, it was a big honor when Fenji kind of suggested that. I immediately answered. I was thrilled, and I'm like, yeah, certainly I would like to do that. It's always nice to touch base, meet new people, and present our work, really. So that's thank you for the opportunity. I really appreciate that.
Great, thank you. So I'll see you later.
Take care, Oliver.
Okay, take care. Bye bye.
Okay, bye bye.